This problem gives us our stream function. You can see it here. It is 5x squared times y minus 5 over 3 times y cubed. And what we want to do is we want to find the velocity potential phi. So let's go through and do that. First thing we need to realize is we can find our velocity components u and v using both the stream function and the velocity potential. So we know that u, which is the x component of velocity, is equal to the partial of the velocity potential with respect to x. And we know v, which is the y component of velocity, we know that that is equal to the partial of the velocity potential with respect to y. Now at the same time, we also know that u is equal to the partial of the stream function with respect to y, and v is the negative partial of the stream function with respect to x. So we're going to use both of these to solve our problem and find phi. So first let's start with these equations over here using stream function because that is what we are given. Let's start by looking at u, and in doing that we need to find the partial of the stream function with respect to y. So if we look up here, and here's our stream function again, circled in red. If we take the partial of this with respect to y, what we're going to get then is 5x squared minus 5 times y squared. And we can also write that that is equal to the partial of the velocity potential with respect to x. And we know that because we have these two relationships. If both of these are equal to u, they have to be the same thing. So we can make this relationship here. Alright, so let's go through and we'll do this one and then we'll go over and look at the v component next. So let's take this right here and we're going to cross multiply. And if we do that, we're going to get basically the derivative of phi, or the velocity potential, is equal to 5x squared minus 5y squared times dx. And then we have derivatives on both sides, so of course we're going to integrate both sides. If we do that, we get that phi is equal to 5x cubed over 3 minus 5x times y squared, and then plus some constant c. So this is what we get when we look at the u component, or the x component of velocity. Now let's do the same thing, but we'll use v. So notice that v is going to be the partial of the velocity potential with respect to y, and it's also going to be the negative partial of the stream function with respect to x. So let's write it right here. So the partial of the stream function with respect to x is going to be negative 10xy. That also has to equal the partial of phi with respect to y. Okay? So same thing we did before, we're going to cross multiply. We're just going to use this part of the equation, and then we will integrate. So here if we do this, we're going to have the derivative of phi, that's going to equal negative 10xy times dy. Integrate, and then we get that phi is equal to negative 10xy squared over 2, and then plus c. Now we can simplify this down. Obviously 10 divided by 2 is 5, so we can write that phi is equal to negative 5xy squared plus c. So this is what we get when we look at just the v component of velocity. So we've got two equations for phi. Now if you notice, we've got same term here. We've got this negative 5xy squared here, and we also have it right here. So that means when we do our superposition, we add these up. Our final equation for phi then is just going to be 5x cubed over 3 minus 5xy squared plus the constant c. Right? So there's no need to have the negative 10xy squared because we just need the negative 5xy squared in there, and we already have that. So that will be our final velocity potential.